So this first lecture, I just want to set the stage for what to expect. I'm not going to sugarcoat anything, but I'm also going to tell you that if I could do it, if my advisor could do it, if Maher could do it, if Dallin could do it, because they're kind of doing some of that, and if you've done it before, then we all could do it, right? It just takes some commitment and effort. It is a serious course. There's a lot of ingredients that go into it. So this lecture, I will start with some motivation that I also use in some of my other courses. So traditionally, the scientific method is based on making observations in the world. So we will take our favorite dude, Mr. Isaac Newton. He noticed that things fall to the ground. Now, he wasn't the only one to see that, but he was the only one to make something called a hypothesis. He said, why do objects fall to the ground? There must be a force proportional to the mass, to the acceleration, of the object. There must be a force. What is a force? He came up with that concept. He made a hypothesis out of the blue, okay? Or a model, call it a model, for why things fall. You know, there's a gravitational force. Force is proportional to acceleration, and that constant of proportionality appears to be mass. And then that's kind of the traditional scientific method approach. Then you go ahead and do experiments. And with experiments, you try not to prove your hypothesis, actually to disprove it. So when somebody tells you the theory of gravity or the theory of evolution, they say it's only a theory. No. A theory has already been proven or has not been disproven yet, okay? A hypothesis is something that you're setting out to prove. Okay, so when you hear the theory of the Big Bang, it's kind of already been demonstrated or hasn't been proven wrong yet. So you proceed to do experiments to validate your hypothesis and try to disprove it, see where the limits are, right? And, you know, like drop things from a tower, right? Dropping things from a tower. Who was the guy who did that? Galileo, was it Galileo? Yes, Galileo, okay. And by the way, and then you refine the hypothesis, okay? As you collect data, maybe, you know, there's an error here, maybe these are the limitations, maybe you cannot drop things from way up in the atmosphere or whatever, right? Now, by the way, this is called the Tower of Pisa, not pizza or piazza, right? So it's the Tower of Pisa, okay? So not pizza or piazza. Now, okay, great. This sets the stage that to do science, you need to do experiments and you need to observe reality. And that's really true, and that's been true since the birth of science, right? However, like, how do you experiment on an exploding star, for example? It's really very dangerous. Like, nobody experiment on like blowing up, you know, doing supernovas at the university. You can't do that, right? Not only is very dangerous, probably you cannot do that. So how can you run an experiment? How can you study an exploding star? You can observe in the universe, but have you seen those pictures from even the best space telescopes? They're like 3 pixels. And they tell you, oh, look, there's an accretion disk over here. And I was like, how do you see that? It's like 3 pixels, right? And we're like, yeah, you know what? This is all our theory, what it does. But it turns out that those pixels and whatever they're seeing, they're actually based on what we're going to talk about here today, simulation, okay, simulation science. So how do you experiment on a hurricane? You could do a scale model, but it's really hard to do like a hurricane in a scale model, all right? So it's easier to do it on a computer. How do you simulate a nuclear accident, for example, right? Okay, you learn from history, or like, you know, you can't, it's unethical to start a tsunami, for example, to cause a nuclear accident. You know, it's dangerous. How do you experiment on a coal boiler? Something as simple as a coal boiler is really hard to instrument, because your instruments will burn instantly, right? So how do you get measurements and readings? Flameless combustion, that's combustion. I didn't know that like until like 6 years ago that this is a thing. Apparently, you could have a room that has combustion in it, but you don't see a flame. So you're there and you'll instantly combust without a flame. So called flameless combustion. Apparently, you know, it has lower emissions, etc. Precipitation, like this, if you've ever been in Lebanon, there's this underground cave, the Jaita Grotto. It's got like these beautiful things coming from the ceiling. This turns out it's just calcium carbonate deposits, right? So these come in through centuries and hundreds of years of depositions. It's the calcium you see sometimes calcium build up on your faucet, right? If it's been in use for a long time. So similar thing. So how do you experiment? Whether you just sit down and observe and write a note for your great-grandchildren to collect data and publish it, right? It's ridiculous, right? So in other words, it's expensive, dangerous, and impossible to do things like that. Now, simulation is a new kind of science. It's still relatively new because it's really took off just recently in the last century, and in the 1970s, truly it became more mainstream, the idea of simulation science. And with simulation science, you augment that picture of the traditional scientific method, whereas now, from experiments, you deduce basic laws, right? So with experiments, it's easy to do experiments on getting the shear viscosity or the viscosity of a fluid, right? But that's it. Like you take that now, you take those data and you put them together with other simpler models to build a more complex model to do, how two galaxies could collide with each other, right? So, and that is where simulation comes in. It couples all the basic laws and models that you've deduced from your experiments and hypotheses, and you analyze their nonlinear interactions, okay? Now, obviously, there's a lot more that goes into it because you need to make sure that what your the simulation is actually giving you realistic results. And we're going to talk about that a lot in this course. So more and more, this is generated by ChatGPT. It says, theory, the first pillar of the scientific method, experiment as the second, this is ChatGPT, okay, second pillar of the scientific method, and finally scientific computing or simulation science as the third pillar of the scientific method. So, and this is a testimony to the power of computing, really. It used to be just these two, theory, analytical methods, and experiments, right? Okay. Now, when you think about simulation, there's no simulation that touches your heart and your soul better than a fluid flow simulation. Seriously. Why? Because it's in our veins. There's fluids in our veins. We move within fluids, right? The air, the water. You see a fluid simulation, it's beautiful. It's mind-boggling, right? And that's why I love CFD too, because I want to make some cool simulations. So I'm going to start showing you some eye candy, some of the work that me and my colleague have done over the years. This is an actual simulation of a coal boiler that is downtown that we were doing. What you're looking at here are injectors. These colors here, they represent coal particles that are entering the domain. They're diluting, so the color represents concentration. And they're diluting and also devolatilizing and burning subsequently, right? So they come in. Now, this is a 3D volume rendering. You don't see much. It doesn't look super nice. But what I want to do is take a slice over here on this plane. I'll show you. So if I were to take a slice over here down there, we were able to take a picture of what we call the fireball inside the coal burner. So these are inside the coal boiler. So these are tangentially fired streams with coal particles that actually come in, devolatilize, and burn. And they heat up. You see around here there are water pipes all over, and they turn the water into steam. The steam goes and generates electricity. Okay. And now this is a long time exposure. It's actually like almost a second, but this fireball is so fast that you see it's kind of like an average of what the flow looks like. Okay, so I'm going to take my simulation and superimpose it on top of that. And this is starting. Now remember, the simulation is in 3D, so there's flow also into and out of the thing. But look how cool that is. And how it starts forming that fireball. And when I take the average of my calculation and do a quantitative analysis, visually it looks right on top of it. And quantitatively, it is actually right on top of it. So we got that right. Okay? Isn't that cool to do something like that? That's pretty cool. All right. This is a volume rendering of a pool fire, courtesy of Professor Phil Smith. He used to run the Institute for Clean and Secure Energy here at the U. So we were part of that group. So our code belongs to the codes that do these kinds of simulations. This is a flare in cross-flow calculation. So this is just the column for the flare. I'm not showing the flare here, but this is showing only the vorticity transport around that. And like these are very complex calculations, but yet like very beautiful. So we were looking here at drag on flare farms, or if you want, wind farms, just to try to understand what's, what the complex fluid dynamics around those structures. Okay. Now it's no surprise that we like fluid simulations because the fluids are in our veins, right? They're everywhere around us. I like this stupid list of things like, yes, fluids are in internal combustion engines, in airplanes, around airplanes, in vacuum cleaners. I don't know why I chose that model. Dentistry tool. I've been doing some dental work recently, so that was great inspiration. And pressure washers and cleaners, coal boilers, etc. Okay. So why do we need computational fluid dynamics? Beyond that, it's so cool, and like I do CFD, right? Beyond that, so why do we need CFD? It's because the behavior of fluids is very difficult to study and predict. For those of you who took fluid mechanics with me in the fall, or who have taken fluid mechanics even undergraduate, you recognize this like, man, this is a complicated discipline. Like nobody understands fluids. It's like quantum mechanics. If you think you understand fluids, you don't understand fluids. There's like so much complexity, yet the equations look somewhat benign. But they're very complicated to predict because the equations themselves don't tell us the story of what will happen in reality. They just have convection and diffusion terms and pressure terms, but it doesn't tell you how to form a Barber's vortex or to show reversible flow for Stokes flow, right? You can't see that directly from the equations. You can't see those. You have to set them up, set the problem up, okay? Now, since fluids are at the heart of many things, right? The fluid mechanics is an important field to study. And so there are three ways to study fluids: theoretical, experimental, and computational. So that's the scientific method, but now we're adding computational over here, right? So we'll go through each one of those again, kind of trying to set the stage very easily. Analytical methods are limited in scope to simple geometries, like approximate the chicken as a sphere, and see what happens, right? Or approximate, I don't know, the giraffe as a cylinder and see what happens, right? So limited geometry. They're very insightful. Poisson flow, one of the most important results in fluid mechanics, tells you the relation between pressure drop and flow rates, etc. It's a simple approximation of like an infinitely long pipe, right? And so, but is it close to reality? Pretty darn close, right? But we have to add corrections to it. It's still pretty useful, but that's the limitation, right? If you're trying to study the complex blood flow in your veins, Poisson flow is not going to be enough, right? It's a calculation you could do when you're flying in an airplane, back of the envelope calculation, right? But that's it. Okay? Anything more serious, you can't use analytical methods. Okay? Experimental methods, they are the most realistic. They're the truth, more or less, but can be expensive and sometimes dangerous or impossible. Okay? Like, again, the example of the supernova. I really like supernovas. And so, so you can't run a simulation of a supernova, right? You can't run an experiment to reproduce a supernova. And finally, computational methods, they're kind of a virtual experimentation based on these first principles. Remember that picture I gave you of the scientific method where we had observation basic laws? We take those basic laws, put them together. So those basic laws are going to be mass conservation, momentum conservation, energy conservation. And we turn those equations into, we have the computer add them. We turn them into little differential, finite differences, etc. And then we try to solve them, okay? Now, they also suffer from numerical errors. There's formulation problems and other headaches that we will observe in this course as well. We will learn about dispersion, diffusion errors, instabilities, etc. But, there are ways to get over those issues. So I put a table for you here looking at analytical, experimental, computational pros and cons for each. And then you ask yourself, okay, what is CFD? Again, a picture generated by ChatGPT. I told ChatGPT, I'm teaching an introductory lecture on computational fluid dynamics today. In your opinion, what is CFD? Like, if you want one image to describe computational fluid dynamics, what do you what would you produce? And it produced this thing. It's pretty interesting. I don't know what's going on over here. Some weird multiverse thing going on, but okay. There's a great definition that I take from Professor Gretard Tryggvason. He's a great teacher and educator of CFD. He was the former editor-in-chief of journal Computational Physics, and a very dear friend. I learned a lot from him. And so he says that CFD consists of computing multidimensional flows, so in 3 dimensions, 3D flows, 2D or 3D flows, by solving the Navier-Stokes or Euler equations. These really are the two equations that we will be, two sets of equations that we will be dealing with. Okay, now Navier-Stokes could be fully compressible or incompressible. Okay, the Euler equations are just inviscid. Okay, so the Euler equations automatically, because of lack of viscosity, they will form shock waves. When we get that in the second part of the lecture, I'll explain to you how a shock wave gets formed in the lack of diffusion. If you think about it intuitively, diffusion tends to equalize things, just smooth things out, and convection is trying to move things very quickly. When you take out diffusion from the fluid equations, you just have only advection. And if you remember fluids, you had this term that's multiplying the velocity by the gradient of the velocity, and that term tends to form shock waves. It's like moving the fluid in two opposite directions. Okay, and it forms a shock wave, or starts creating like things that are spinning. Okay, let's go back to this definition. Navier-Stokes equation, Euler equations, with the goal of obtaining both physical insight into the flow dynamics and quantitative predictions of engineering flow systems. Now, CFD is one part of a bigger picture. It is the most popular, by all means, because it is the most captivating, right? It is the most captivating. You could show a molecular dynamics simulation. Look at molecular dynamics simulation. I'm like, these particles that are like just wiggling, these molecules that are moving in place, right? And you know, it's not relatable, right? You see a fluid simulation, like, oh my gosh, this is beautiful, right? And so it's just very popular, right? It became very popular, but it's part of a bigger umbrella of scientific computing, where you could have solid mechanics simulations, simulations in chemistry, simulations in physics, material science, etc. Fluids is scientific computing. CFD is scientific computing applied to fluids. Now, we anecdotally call everything CFD, even when we're doing solid mechanics. They're just doing CFD, they're just doing CFD. And sometimes I call someone, I like your CFD. No, sir, this is molecular dynamics with solving the Boltzmann equation. It's just all CFD, And so, yeah, I like to mess with people that way. But, okay. Fluids, CFD. Now, as a discipline itself, CFD is very multidisciplinary, okay? My attempt to do a Venn diagram, I think I created this, whatever the thing for, anyway. So for witchcraft, right? Like these three things. Okay, so CFD has 3 critical ingredients. Fluid dynamics, these give you the equations and the physics, the understanding of the physics. Numerical methods, how we can take those equations and convert them to something that a computer can compute, and then putting those new transformed equations into a computer. That's where computer science comes in, but not really computer science, but yes, computer science, because programming is not computer science, okay? So give the analogy. You can drive a car without having to understand the internal combustion engine. You can be a programmer without being a computer science, and you should be, because programming is just a tool. It's just like a car. As an engineer, you need to know how to program. Right in this day and age, that's the reality, right? It's already hard enough with AI, right? Competing with AI, so you will have an edge, right? And so, but in modern CFD, there's more computer science, because now we're like trying to figure out how we can index an array. Like, should we go in the IJK direction or like JKI? How is memory laid out? So you get into some mind-numbing computer science stuff that's like beyond what we really need to get something working. So I call it computer science, okay? I want to go through some historical perspective. Some of you might have heard of these words thrown around, but most of you have not. But I like to have that historical perspective just for your own benefit. If one day, you're just kind of walking and bored, you grab those papers and start reading them as you do every day, right? Just reading scientific literature. Okay, the first attempt at the calculation, and really you should try to download that paper. It's so cute, it's so hilarious because he did the calculation by hand. So Sir Lewis Fry Richardson, a British physicist and atmospheric person. So weather prediction was a big deal at the time, okay? So he's the guy who came with that poem about turbulence. Big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So Lewis Fry Richardson, okay? And this article, the approximate arithmetical solution, look at the British, the approximate arithmetical solution by finite differences of physical problems involving differential equations with an application to stresses in a masonry dam. And then, he has a paper about weather prediction right here. I want to see. I think it's on the next slide. Okay, and so you have a bunch of papers early on in the beginning of the century, 20th century, right, from 1900 to 2000. And so early on, 1910, 1924, right, you start seeing 1928, 1930, a numerical mathematical analysis. Now this particular paper. Let me see if it's on the next slide. It's not. But this particular paper, okay, also by Richardson, weather prediction by numerical process. I don't have it listed here. I have a copy of it, actually. So this is a map of Europe, and he discretized Europe like each grid cell was like 1,000 kilometers in each direction, right? So it was huge. So it was like one grid point. And, he had like 1, 2, 3, 15, 20 grid points. And he did the calculation by hand. You see tables upon tables upon tables of trying to do weather prediction just to solve the equations for the atmospheric flow equations. And so very inspiring. And that's it's not more sophisticated than that. So if they can do it in 1910 or 1920, we should be able to do it now. We have much better tools now, okay? And then there's a bunch of papers that I'm listing here also out of just completion and for the sake of the historical perspective, because I want to get to the 70s. It's really in the 70s where CFD truly took off in the modern sense. Here we were just trying to apply, okay, what do you do with the finite difference method? Can you solve these equations? And they were mostly interested during the Second World War, as we got close to the Second World War, understanding ballistics, right, in the air and aerodynamics and all of that stuff. So there was a lot of work on the Euler equations, the inviscid equations, which are very hard to solve because they form shock waves. So a lot of the shock capturing methods, if you've heard of that word, they come from this work. Okay? Iterative solutions of finite difference approximation to elliptic equations. Again, Richardson stability analysis for PDEs. So this is where the Courant, Friedrichs, and Levy condition in 1928, the CFL number, the Courant number, if you've heard of that, 1928. And it's still taught to this day, right? It's like at the foundation, and I will teach you that as well. Point 4, all sorts of methods trying to understand how they solve the Navier-Stokes equations or variations of the Navier-Stokes equations. And at the same time, there was development into the theory of boundary layers, etc. If you remember in fluids with Blasius and Prandtl around that same time, everything, all that stuff coming along together, right? The product of its time. But CFD in the modern sense really started with the formation of the T3 group at Los Alamos National Laboratory. And early development in the group focused on compressible flows because they were trying to understand aerodynamics, okay, and flying at very high speeds. Really, that's what really set the US apart from the rest of the, even to this day, air superiority. There's no country that matches air superiority of the US because of the understanding and the knowledge we have for compressible aerodynamics. The first method was particle in a cell, or PIC method, 1955. We're not going to learn that. This method evolved significantly. And then they tried to do some low-speed flows. They had issues with the pressure because, as we will see later, there's no equation for the pressure when the flow is incompressible. For a compressible flow, you have momentum and continuity and an energy equation and an equation of state. So everything, you have all the equations on all the unknowns you need. When the flow is incompressible, as you will see, you don't have an equation for the pressure. You just have 4 equations and 4 unknowns, but no equation for the pressure. So how the heck do you solve for the pressure? They didn't know. So they come up with vorticity stream function formulations. And then they came up with the marker and cell method, which was the precursor of the staggered grid, which we will learn in this class as the best method for doing computational fluid dynamics. Okay? And then all-speed flows with an implicit method called ICE and arbitrary Lagrangian methods. These are words. I don't even understand all the methods presented here. Like, I know how ICE kind of works, but I don't know it. But I can learn it, right? And so you're not going to learn ICE or ALE or free surface flows here, but you will learn enough so that when you go out and doing a new application, you know the language, the terminology, and you can apply yourself to those methods and learn them and apply them. All right? Okay, some of the early development, and I think this was ASCII art. This is a flow over a blunt object from and Harlow, also kind of well known in computational fluid dynamics. The MAC method, which is the marker and cell method, which was the precursor of what we call the staggered grid. Again, it's a very important technique that we will use in this class. It used to be called the marker and cell method. They did the first dam breakup simulation. What you're looking at here is a bundle of fluid. I know these look so ugly and old, but I want to show you like how far we've gone, right? So you have just some fluid here with a little barrier, and then suddenly you lift the barrier, and due to gravity, that fluid is going to come down and slosh around in this container. So that's very important when trying to study dams, and also when trying to study transporting gasoline in big tanks, right? As they slosh back and forth, they could create really hazardous situations. These are also, this was featured in Scientific American, Computer Experiments in Fluid Dynamics in Scientific American. Can you imagine that? That was like a big deal, really big deal at the time. Now, I have an excerpt here from a memoir by Harlow, who's the guy who was behind many of these methods, the marker and cell, et cetera, Francis Harlow. And it's really fascinating. It was published in Journal of Computational Physics in 2004. I'll read a little bit with you. Again, I won't bore you with these details, but I think they're kind of just important to appreciate where they've been and where we are right now, and as we take CFD for granted. So many of these results were published in reports and journal articles, but not without some opposition. There was, for example, a conversation that was reported to me which took place around 1955 between two of the upper-level managers of the theoretical division, one of whom said, "Look, what is this stuff?" Right? Like, what's the crap? What are they doing in this group, in the T3 group, which was supposed to be doing CFD? This PIC, particle in cell method, that they're trying to publish a paper on will never work. That's the worst statement you could do. The fact, I tell my PhD students, when they come and tell me, this cannot be done, I tell them the fact that you cannot see it only means that you cannot see it. Doesn't mean there's no other way to do it. Never say will never be some. Don't be on the bad side of history, you know? Okay, so seriously, like, so Lord Kelvin, did you know what one of his biggest quotes that nobody talks about, but I have it in my dissertation? He said, "Machines heavier than air will never fly." And gosh, he was so wrong, right? So obviously airplanes can fly, right? Okay, so he said this will never work. Obviously, this PIC led to the marker and cell method, and you know it's the foundation of modern CFD. And then there will never be computers big enough. Seriously, there will never be computers big enough. We are heading there really fast. Big enough and fast enough to solve problems with all the particles that you need in order to resolve what's going on. So the particle in cell method, in a way, was trying to model fluids as a collection of particles. To really get a good statistical sampling, you would need billions of these particles to keep track of them. Okay? But because they were using a Lagrangian perspective, they were trying to follow the fluid. But the simple shift was to go to an Eulerian perspective and not follow particles, rather fix a region in space and study what's coming in and what's leaving. And that solved the entire problem overnight. That's the Eulerian method. That's the marker and cell method that they evolved from this. I don't think we should publish this. And the other person said, hey, look, maybe it's not useful or won't work at all. But on the other hand, it's something that was tried and, something that people will learn from, probably mark it down. It'll go down in the annals of things that we tried and never worked, etc. Okay? So I'm happy that the second point of view prevailed. Now, another type of opposition occurred in our interactions with editors of journals and with scientists and engineers at various universities and laboratories. One of the things we discovered in the 50s and 60s was that there was a lot of suspicion about numerical techniques, and that's good. You need to be suspicious, okay? You need to be skeptical, but not to the point to exclude yourself from the power of numerical methods, right? You need to hold it accountable so that it's valid, it gives you results that are realistic and correct, not just a toy, right? So I'm guessing that's what they wanted. Now, computers and the solutions you could calculate were said to be the playthings of rich laboratories, right? You couldn't learn very much unless you did studies analytically. The truth, of course, turned out to lie in the complementary interaction between calculation and analysis. So really, you run a calculation, you look at it, does it make sense? Like when we did in numerical methods, when we plotted the heat transfer in the rod. And then we said, well, the boundary conditions make sense. Is the temperature going to infinity? That, right? So analysis is important. And then they did verification, which we also did in class. We would verify things on simple problems, test our methods on simple problems. The truth, of course, turned out to be in the middle. I think some of these early suspicions were justified anyway. So it's a fun memoir to read. I'll put the paper. You can download it. I'll put it on Canvas. Okay. Now, really, in the 70s, CFD goes mainstream. That's kind of where we start, recognizing what are the methods that work. It was post-World War II. The world was booming. Technology was advancing. It was still not impressive to the public because the fact it needed an expert user to do CFD. Nobody understood what these guys were doing, right? And robustness was key. If you don't care much about accuracy of the answer, but you don't want your code to crash in the middle of the night, we need something called very diffusive schemes. And this is what came about around that time. We started seeing commercial software like Fluent, StarCCM, Open. These are very recent, actually. So COMSOL, pretty recent. OpenFOAM is an open source code, et cetera. So these big commercial codes made it accessible to the public. But unfortunately, it dumbed down a lot of the complexities of the calculation, because for someone using CFD as their tool just to hey, how's the airflow in this room, but they're not a fluid mechanics person or a CFD person, you don't want that software to crash. How frustrated are you when Word crashes or when Adobe crashes on you, right? That's still a piece of software that needs to be used by someone clicking a bunch of buttons. You don't want it to fail. So the numerical methods that went in there were very diffusive. You will learn about that. But also meant it took out a lot of the accuracy of the calculations. Okay? But that's what actually helped CFD become more popular with the public. When we integrated these CFD calculations into solid mechanics tools with ANSYS, for example, et cetera, then that gave the designer, the average engineering designer, oh yeah, I could do fluid analysis over here. I could do structural analysis over here. I'm designing a fender for a car, et cetera, right? And, they didn't know what was going on behind the scenes, but they got some pretty looking pictures about the stress distribution, how the velocities, and it was reasonable, right? And in that sense, yeah, it worked, and it helped CFD become more of what it is today. Now, today things are different. And CFD is more respected and is actually a part of an engineer's arsenal. And in many cases, they would ask us in a publication, where's your numerical validation, right? Which is great to hear, right? Okay, they did experiments, they did theory. Where's the numerical validation? Did you try more complicated cases with your numerics? Why didn't you solve the harder equations, right? So they're asking more. Why did you solve this simplified model? You could solve more. So do the full model, right? And so it's a good thing. But why did it become more respected? What changed? It was really computational power. So this is from 2021. There's a website called top500.org. This is not the most recent. It ranks the first top 500 supercomputers in the world by order of how many floating point operations it does. Okay. So what's a floating point operation? It's anytime you do something with two numbers: addition, subtraction, division, multiplication. You could say multiplication is more costly than an addition, etc. But on average, in a typical, just call them one flop, one floating point operation. So anytime you have a division, multiplication, addition, or subtraction, you have a floating point operation. So the more floating point operations you can do per second gives you a measure of how strong the computer is. So what you're looking at here is in teraflops, okay? Teraflops. So this is 442,000 teraflops, this Fugaku Japanese computer. And then Summit and Sierra, they from IBM, come in the US, and then Sunway in China, and so on. Now, the list has been updated in 2024, but I couldn't find a plot in Statista to do that. Anyway, so that computational power is what changed. Remember that statement in Harlow's memoir about the upper management guy said, computers will never be strong enough to solve this problem. Well, they are, okay? In fact, they are, and we're getting there, all right? Okay, so what are the ingredients of computational fluid? What do you take to make this, right? So obviously, you know, tomatoes and vegetables and bell peppers and things like that. So what are those ingredients? There's like 3 simple steps, and each one of them is going to take hours of lecturing and study. We need to identify the physical process we're dealing with. So we'll discuss that next, like is your flow laminar, turbulent, compressible, incompressible, etc. Figure out the mathematical model you want to use. Are we going to use variable density or constant density? Are we multi-phase or single phase? Is species diffusion important? Is this flow reacting? Are the reactions important or not, etc.? Identify a correct mathematical model, and finally develop the numerical model, put it in your code, write a code for it, or just use it in your code if it's already available, and do a calculation. Okay. So identify the physical process. Is it compressible, incompressible, laminar, turbulent? Or is there combustion? Are there reactions? Are there moving geometries? And then develop the mathematical model and the solution algorithm. Usually a set of partial differential equations. Those are Navier-Stokes or Euler equations by definition, because this is computational fluids. Okay, so you'd be dealing with the Navier-Stokes equation. In this class, we will be dealing with the incompressible Navier-Stokes equations, at least initially, so that we get you, moving in the right direction. In your project, you might choose to do a compressible calculation if you want, if we have time. We'll cover some of that also if we have time at the end of the semester. But for now, we will be essentially focused on laminar incompressible flow. Turbulent flow is a piece of cake once you know how to do laminar incompressible flow. Now here, the step could include additional assumptions, symmetry, constant coefficients, etc. And also the algorithmic steps needed to solve the model. So we will learn about the method called the projection method that allows us to find an equation for the pressure. Remember, I told you there's no equation for the pressure. And bear with me, I'll solve the equations in a second. And finally, develop a numerical method and algorithmic procedure to solve these equations. Usually, it's either finite difference or finite volume or finite element methods. There's spectral and boundary element methods. Those are not as popular or robust as really the finite volume or finite element methods. In this class, we will start with finite differences. I'll explain my philosophy in a minute, and get to finite volume methods. All right. Here's an example. Consider like the flow over a square cylinder. This is a problem I did in my undergraduate thesis project. And I was fascinated by how, if you remember the Tacoma Bridge, which was a problem in graduate fluid mechanics, right? So this is a famous bridge that collapsed in Tacoma in Washington, right? That's what it is. And in the 50s, it just started vibrating, oscillating, and then it collapsed. So let me show you the video. See the bridge oscillating. There were no cars on it. Nothing. It was just very high crosswinds that caused vortex shedding and caused the bridge to oscillate. We solved this problem in graduate fluid mechanics. It was a nasty homework assignment. So, yep, there's a lone car left on the span. I don't know if you can see it, but like there's a guy, I think, walking here, no? Yeah, he's running. And now the road break, yep, and then catastrophic failure. I'm sorry, this is like the best resolution I could find. It's insane to see that. So this is a fluid structure interaction problem, obviously, but it was primarily driven by what we think the problem is that the airflow, the crosswinds across the bridge caused these oscillations, and it just caused this feedback loop, and the bridge collapsed. Let me see if it's any longer. Like what, 17? Okay, so let me. Okay, here's the collapse, okay? Total collapse. Love the exclamation mark. All right, the whole thing collapsed. Okay. All right, so let's move on. These are the equations that we will be solving, okay? And I will explain, we will derive them in an intuitive way. We'll spend one lecture deriving them, but they're just equations. They're just differential equations. These are the Navier-Stokes equations for an incompressible laminar fluid with constant properties, so constant density and constant viscosity. These are shown for a three-dimensional flow. So you have x, y, and z directions. For practical reasons, we are going to do the two-dimensional version of those. So we will cut down one equation and one unknown. So there are four unknowns in these equations: the u, v, and w velocities. So those are the speeds of the fluid in the three different directions: u, v, and w. What is the speed if the fluid is moving in this way, right? So what is the speed in the x direction? Call that u. In the y direction, call that v. In the z direction, call that w. Okay, so those are u, v, w. But there's also this p, pressure, which we don't know. Okay, so what is the pressure at every point? Given some conditions at the boundaries, how does the pressure change in this room or as the flow is moving? Okay, mu is viscosity, it's constant. Rho is density, it's constant. We'll explain those terms later, but like you see, kind of a lot of nonlinearity over here. You have u du by dx, so that's what? A nonlinear term, okay? Because it's u multiplying its gradient. And then you have v du by dx, so that couples v, the v equation, to the u equation. That's crazy, right? And then couples it with w. In 2 dimensions, we will knock out the w equation. Okay, so we'll do only in xy, so it simplifies things quite a bit. Excuse me. And then finally, you have this last equation called mass conservation. It's just a statement on saying that the sum of the gradients of the velocity in each direction, or the divergence of the velocity, is 0 at every point in the flow. So that tells us what we call mass conservation, and we will derive this equation as well for those who haven't seen it before. But when you look at these equations, I'm going to write them now in compact form, in vector form. So that's where your vector calculus needs to come in. Frankly, we will be really dealing with these because we need to program each and every term. But when we talk about theory, we might have to switch back to the vector form. So when we switch to the vector form of the equations, if you write the u velocity vector as uvw, so ui plus vj plus wk in the three directions, Cartesian directions, then those equations, they collapse into just two vector equations. This is a scalar equation, div u equals 0, so that's the mass conservation. And then the momentum equations over here. So if you put u here, you put u or v or w, you substitute u and v and w, and you get all the previous equations in very promptly. But what I want you to focus at here is that, okay, I can solve this equation. Let's go back maybe here. Okay. How do we solve these equations? It's frankly a nightmare because, okay, let's say I can solve the first equation for u, the second equation for v, the third equation for w. But where is the pressure? Could we use the first equation to solve for the pressure? But there's the pressure in the second equation. Why not use the second equation? No, you should use the third equation to solve it. Can you combine them to solve for the pressure? What about this equation? We haven't used this equation yet. You can't use this equation to solve for u and v and w because they're equally important. You can't actually invert that equation. It turns out that, no, we're going to need these equations to solve for u, v, and w, and we're going to convert this equation into an equation for the pressure. This turns out for incompressible flows that the pressure is your free parameter that allows U and V and W to satisfy this equation. And that's a method, that's the method that we will learn in this course, okay, to solve these equations. Okay, this is another, this is actually a paper about a full fluid structure interaction simulation of this Tacoma Narrows Bridge and showing the oscillations. So you can see how in their fluid structure analysis, how they did this. Anyway, okay, now you do CFD. Let me just make sure I'm good on time. Okay, very good on time. There's two steps also in CFD that people don't talk about, and I hope we'll have time to talk about them. We might be a little bit shy on talking about those, but they're important. And they're called verification and validation. They're different. Don't confuse the two with each other. You've probably heard those words thrown around. They have very distinct meanings. Verification answers the question, does your code solve the model you proposed? Not any model. You ask the question, okay, I implemented a model to do, Fickian diffusion. Does my code solve that problem? That's the only question that verification does. How faithful is the software implementation to the original mathematical model? Are you adding new terms in the model just to fix things? So oftentimes you end up trying to hack your boundary conditions. And by doing so, you actually mess up your governing equations. And you're actually not solving the equations that you thought you were solving. So that's verification. Verification doesn't check if your equation, if your numerical simulation is actually related to reality at all. It doesn't matter. I don't care. I could have a spherical chicken in space or going into a black hole, which is, never happens, right? There's no chicken kind of flying into black holes. But, that could answer the verification question, right? Validation is where you ask the question, does my model faithfully represent reality? So compared to experimental data, compared to observations, compared to theory, does my model actually capture reality? And that's where you have like errors and so on and so forth. Okay? So two different things. And it's a whole field by itself. Okay? All right. So now the question that everyone is kind of waiting for me to talk about. What do I need to do CFD and to do well in this course? I want you all to learn, okay? This is not, again, it's not an undergraduate course, okay? I want you here to want to have a discussion. We want to learn. I'm assuming that you're all coming here by choice and you're motivated to learn about the material. But I'm not going to sugarcoat it either, because it's like one of those fields that like you have to know these things to do the bare minimum in computational fluid dynamics. You need to have a strong knowledge of fluid mechanics, okay? Now, I know some of you have not had the advanced or grad fluids or haven't even had fluids, okay? The strength in knowledge of fluid mechanics comes when you are interpreting your results. So when I first taught this course, we had a heated driven cavity, which is going to be your first project. You're going to do a driven cavity with flow inside it. We're going to heat it on the sides and have like convection streams coming up and causing buoyancy and all sorts of fun, interesting things. And the lid was moving in this direction, but their flow was in the opposite direction. Okay? Now, they knew fluids, and they should have said, like, this doesn't make sense, right? And so that's the extent where I say strong knowledge of fluid mechanics is like being able to interpret if your results make sense or not. Now, is this going to matter so much in this course? To a certain extent. But if you're able to accept the equations that I showed you previously and my discussions about them and ask questions about why does this term look like this, why that term looks like that, you'll be fine. Okay? So this specifically to the junior students. Okay? You can also check my YouTube playlist on fluids. It's a big discipline. Okay? Strong knowledge of vector and differential calculus. So this is important. Strong knowledge of partial differential equations. Now, you might not have taken differential equations. I'll try to teach you about differential equations, but I'm not going to teach you the theory of differential equations or lemmas and whatnot. So, leave that to the mathematicians. But what I will teach you about is advection, diffusion, and source terms, right? So an intuitive perspective on differential equations. And if you're able to augment your mind to reach that point, if you haven't done differential equations before, then again, you'll be fine. Strong knowledge of linear algebra essentially knowing how to invert a matrix, or knowing that, oh, I have a system of linear equations, I'm going to invert it, right? So ax equal b means x equal a inverse b, which is, and I talked about this in numerical methods, and I'm glad you are here to see actually this going, to see this in action, okay? Programming, all right? So we will use Python, not almost exclusively, exclusively in this course. And there are reasons why I use Python. First, it's free. It is the programming language of the future, at least for the next 5 years, at least, right? So, you know, it's good to know Python, right? It helps you to know Python. And with Python, we can get these really cool Jupyter notebooks. These are documents. If you haven't done Jupyter notebooks before, these are documents where you can mix text, equations, multimedia, and code in one document. So you don't have to write a report separate from your code, separate from your figures, and drag and drop. You can put everything in one document. Everything is self-contained. So that's why I like that. All our codes will be done in Jupyter notebooks. Now, all you need to do is download Python to your computer and download the Anaconda distribution is the one I recommend. Just Google Anaconda Python. If you have Windows, if you have Mac, it should just work. And now you open the Anaconda thing, there's something called Jupyter Notebook. Just see if it runs, if it opens up. And that's it. Now, do you want a course on Python to be able to do this? No, please don't take a course on Python, okay? Definitely not in computer science, because this is not a computer science course. This is a tool, okay? What is important in programming, so, and this is my philosophy on programming, and my numerical method students know this. There's, just like language, there is language and there's ideas. Language expresses an idea, right? If you think of language, language is like the clothing or the, you know, ornaments around the idea. But an idea transcends all languages, right? I can express in general the same idea in French, in English, in Spanish, in Arabic, whatever, right? Okay? Those are languages, but the idea is the same, right? So what matters is knowing what idea you need to do. So, for example, recognizing, okay, now I need to sort an array. Or I need an array to represent all of those temperatures. How do I create an array in Python? How do I create an array in MATLAB? How do I create an array in C++? Those are the languages, but the idea is the same. How do I invert a matrix in Python? How do I invert a matrix? And how do I plot the sine function? But knowing what you need to do is more important to me. Okay, so if you're willing to say, okay, I'm going to try to figure out the pseudocode, in other words, in my mind, everything we're going to do in class is going to be no different than what you're going to do in your homework assignments, because there's only like 12 things that you need to know in Python. You know, you import NumPy and Matplotlib and SciPy. You'll need to know linspace, Matplotlib, matplotlib.pyplot.plot, right? So plotting utilities. Linspace, okay, linalgebra.solve. We will learn about sparse algebra. We'll learn about kind of indexing, shifting indices, right? But like no course is going to teach you those specifics. So those are very specific to CFD, okay? So I'm not expecting, even if you're an expert in Python, I'm probably going to find a use case where it's going to challenge you, okay? So what do you do in this case? You know, it's up to you. If you feel comfortable with concepts of programming, like, yeah, you know what, I understand that, yeah, I can create an array here and plot. Like to plot sine of x, you need an array for x values. You need the function. You need to apply that function at each one of those points in the array, and then plot those y values. If you can do that in your mind, doesn't matter, then you can do it in MATLAB, we can do it in Python, that's fine, okay? But if you know how to do that programming concept, then you'll be okay, all right? Okay, now, what this course is and is not, okay? Okay, this course will teach you to become a CFD insider connoisseur. And Keynote kept correcting me on connoisseur, turning it into connoisseur. I'm like, no, it's connoisseur. It's a French word. It means a knowledgeable person in the subject. Sorry. I was like, wanted to change it to connoisseur. There's no such thing as connoisseur. So, but the funny part is like when I correct someone about it, they correct me back. Like, no, it's called connoisseur. Like, shut up. Okay. So this course will not teach you how to use commercial software to do CFD. I'm sorry, this is not the course for you. Okay? If you want a course like that, you actually don't need a course. Just go look at the user manual in Console or Fluent, and you'll be just fine. Okay? Because using commercial software is just pressing buttons and doing things, boundary condition, etc., and you'll be fine. Okay? I used to do this. That's how I used to do CFD in undergrad. I had no clue what was going on, but I knew how to use Fluent. I was a Fluent expert. Okay? But I had no idea how CFD worked. Okay? All right. Commercial software CFD users are not necessarily experts in CFD. Okay? Unfortunately. All right? So I was not an expert in CFD. The fact that I knew Fluent by heart was not an expert in CFD. Because if someone came and asked me, what is the projection method? Or like, how do you handle the pressure velocity? I'm like, I have no idea what you're talking about. I let Fluent do it, right? Fluent's got some worker bees in the computer running the calculation for me, okay? So commercial CFD users are only experts in the software, okay? Now, you could be a CFD insider and know how to use software. That will make you both, right? I sometimes use the commercial software to do like quick projects. To start appreciating and understanding CFD, you need to write at least one CFD code, okay? So Maher is on his second or third now, right? You're on your third CFD code. And yeah, last week he came in, he's like, you know what? Yeah, now I get it, And same for me. I used to know a lot of software that did CFD. And not until I wrote my first code that I realized, no, I had no idea what CFD is about. So you need to write a CFD code. And I will help you do just that. So if you stick with me, if you're willing to learn and commit the effort, I promise you in like 4 to 6 lectures, you'll have your first CFD code up and running in your own Python code, okay? All right. This is my CFD mindset. I like to classify CFD people into 3 camps, okay? There is the CFD practitioner. It's the person who uses CFD, commercial CFD software, has cursory understanding of CFD, has never written a CFD code, but knows the inside out of the software. So an expert user of Fluent or Console, okay? That's the CFD practitioner, okay? They're usually in a suit and looking, at a computer, etc. And, there's a lot of people that do that, and that's fine. The problem is once they get into trouble, they call in the experts, right? So Fluent, for example, has an army of CFD practitioners. These are people who know, engineers actually, who know how to use the software. But when they get into trouble or when they try to implement something for a client, and they're like, okay, this is beyond me, right? So they have to call in higher end users, which are generally the second piece, which is the CFD developer. Has an in-depth understanding of CFD principles and has developed at least one CFD code, typically working on creating and improving CFD software. So that's what this course will make you. Okay, at least get you on that trajectory, because you'll come out of this course writing actually 2 CFD codes. The first one, you'll write it with finite difference, and the second one, you will write it with finite volume. And actually, you might have a third one, because by the last project, you might write a compressible code. Okay, so that's a good thing to have on your belt. Okay, so that's the CFD developer. Okay, so now notice, this was a 1 screen. This is like 3 screens. Now this dude is the CFD innovator, is an expert who's written several CFD codes, like almost a dozen, okay? Uses various commercial software and works on advanced open source codes to develop new CFD applications. So, so after you write your first few codes, etc., you're like, okay, now I need more. And there's no time to write very sophisticated, highly parallelizable, codes, etc. So you start using frameworks, like from the national labs, from the University of Utah, etc. You use these frameworks, and you pull in functionality that does mesh generation, that does high-order interpolation, and you blend them together to solve what you want to solve, the problem that you want to solve. Okay, so that's kind of the CFD innovator, that they know everything that they need to do, and they know what pieces they need to pull together. So hopefully, if you end up doing research in scientific computing, you will be a scientific computing innovator. Okay. Plan for this class, 3 parts. Probably we'll do only 2, because summer semester we have, 8, 10 less lectures. How many did we count last time? 22 versus 31. Yeah. Okay. So we have about 10 lectures less than a spring semester. So I had to trim some material from the beginning and the end. Okay, but rest assured, the core material, which is the important piece, you're still going to learn that. Okay. So part 1, you will solve the Navier-Stokes equations numerically. This is we're going to hit the ground running starting Thursday. Okay, by next week, we'll be doing advection, diffusion, etc. The week after, we'll probably have our first CFD code. I promise you that. Okay, so we will solve the Navier-Stokes equations from scratch in 4 to 6 lectures. You will have a simple self-contained solver. We will do the lid-driven cavity problem. You'll visualize it, and you'll be like, wow, I'm awesome. But we will do a warm-up first. We will cover the governing equations. We'll do basic numerics, finite differences. That's it, nothing more complicated. We'll study advection, diffusion. We'll solve the advection, diffusion equation. Because advection, Navier-Stokes are nothing more than advection, diffusion equation with pressure. The way to untangle the pressure is that one extra step. And once you learn that step, you put it in the code, and you're done. Okay? You have your first CFD code. Okay? So that's the plan for us. We're going to start on Thursday. We'll look at the governing equations, and I will explain them from a very intuitive chemical engineering perspective that says, you know, essentially you have always advection, diffusion, and a driving force. And you can apply that to mass conservation, to momentum conservation. That's it. Those are the equations. We take them and move on with life. Then we study finite differences. We apply them to a steady state diffusion problem. We apply them to an advection problem. Then we combine the two. Then we do it in 2 dimensions, right? And then we hit Navier-Stokes. And we'll have all the tools by then as we're building things up to get to Navier-Stokes. Part 2, now obviously here, there's going to be a lot of things that are going to be like, why did he do this? I'm going to tell you, just trust me on this. Okay, you have to trust me because I want to get you to drive the car before you study how it works. Okay, that's the motivation because I want you to have results, right? You have a result, you're excited, you're motivated, you want to know more. Then we're going to go and dig deeper into every piece of what we did. We're going to study numerical dispersion, numerical stability, numerical diffusion, modified equation analysis, all sorts of iterative solvers, all sorts of the nasty little things that go inside every piece of what we did. And you see there's an open-ended world for all the things that you could do in this part. Okay? And then finally, as time allows it, I have a lot of advanced topics that I'd love to talk about. There's more advanced solvers. I want to talk about verification, validation, turbulence modeling, low Mach flows, but they're all an additional piece to this part. Okay, once you do this part, you have the guts of what it takes to do CFD, and you'll be able to analyze and study new methods, okay, as you move on. Okay, if you end up doing research in this space. Projects and homework, that's all we're going to do. Homework is going to be sparse. There's probably going to be 5 or 6 assignments. They can be intense, and I'm sorry about that. But they could be like very lengthy, but they're heavy in numerical mathematics. So I'll give you an equation. I'll tell you, let's do this discretization or this procedure, and let's study the error. Do this, do that, do this, and do that, and do this, and do that, right? And so you'll try to do that. I'll guide you, and they're very rewarding because they demonstrate the power of analytical methods applied to numerical methods, because we can represent the numerical theory analytically as well. Okay, and that's why we do this as a PhD level course, because you're not technicians, okay? You're engineers, and you're beyond engineers. This is, again, graduate level material, right? Course homepage is Canvas. Make sure you have access to that. Your emails are connected. And my YouTube channel, that's where I will post these recorded lectures. They will be under a playlist called uCFD 2024, best CFD class in the world. So okay. I'll use Canvas as needed to put grades and communicate with you, etc. Please subscribe to my YouTube channel. It's called Professor Saad Explains. Like, go today, subscribe to it so you get alerts. Like all the videos, comment everywhere, invite your loved ones, invite the ones you don't love, tell your neighbors about it. Trigger the algorithm, okay? So it ranks the videos higher, okay? All right. Anyway, so enough of that. Okay. Books. I will have versions, PDF versions of those posted on Canvas or chunks of the chapters. I don't draw from one particular book. It's some things based on experience, personal, my own way of interpreting things, what I've learned from great teachers. But this is a critical book that helped me a lot, Computational Fluid Mechanics and Heat Transfer by Pletcher and Anderson, and we call it Tannehill, the Tannehill book. doesn't matter what edition you get. If you find a used version on eBay, just grab it. It's a nice little book to have with you. I'll upload some PDF, some of the chapters. Same thing for this one, for Anderson. All right, expectations. This is a graduate course. So I expect you to produce graduate level, high quality results. So in your products, in your reports, or your presentations, we're not going to have reports for projects. So just a presentation. Okay, I know you're busy and you don't have time. But the homework assignments, I expect you to, put a serious effort into them. And, we can talk about what's going on with the homework assignments. And, with Maher, and between Maher and me, we can fill in the gaps. Definitely, Maher, just go ask him the hard questions. Okay. There's no project reports, like I said. I expect you to be a great team player or leader. So we'll form teams for the projects, and you can work together to get the results and present the results together to lessen the burden. I expect you to be professional, all your communication with me and the rest of the students, and I will do the same for sure. And, this is one other thing. This is not an undergrad course, so there's some question where say, I don't know the answer, right? It could be this or could be that. It's just different methods that produce different results. So that's the graduate mentality. It's an open-minded, open-ended mentality. Okay. Now, I'm sorry I have to mention this, but I have to mention it. Copyright issues. So these slides and videos are creation and intellectual property of Professor Saad. Okay, so let me explain that. And they are, so whatever I share with you, they're for your own personal use. Okay, so remember, ideas are not copyrighted, right? So finite volume method is not copyrighted, but the way it's presented, like once we get to finite volume and you see the slides I put together, I spent over 48 hours literally just to make like 7 slides with the animations and all of that, and deleting and putting the content together, right? It takes time for that to be created. And the last thing I want is, which happened last year and the year before, like my slides were being sold on Scribd or one of those platforms, and I have like this silly little copyright here, like it was all blanked out. I'm like, come on, guys, So I took down my entire website off from the internet, and because you know what, this is for fair use for everyone to use it and learn it. But if you're gonna abuse it, then you know what, I'm not gonna share it, right? So whatever I share with you, please keep it for your own use, for your future use, for reference. Don't put it online. Do not share them with others. If you want to share them with others, just let me know, okay? Or like in Fluids, I had one of the students send all my lecture notes to another professor in another country, and I discovered, just at least tell me. I'd be happy to share them with you. Let me give you the problems, because first, I don't like the quality that the student sent, because I have a standard. Like if I'm sending you a document, it needs to meet a standard, right? And if you send the document on my behalf, that's not the standard that I approve of, right? But I'd also like to know, that someone is using my work, because I use other people's work as well, right? And I cite them if I use it in the same form. If I inspire from them but redo my own, right? I also still cite them, right? Inspired by, or someone said this or that. So do not post them online, definitely online. Please, no Scribd or Chegg or whatever. Definitely don't sell them, because I want to sell them. But please don't sell them. Do not claim them as your own. You might want to pick a slide and say, okay, this is from Professor Saad's course. This is the staggered grid, like the staggered grid that everyone uses in our group. So ask Maher. We have copies upon copies of the staggered grid. And it literally took me like 3 hours to build that grid arrangement. You'll see it. You'll be using it to do all the nomenclature for the work. So is it like the only staggered grid in the world? Of course not, right? But this is like my creation, right? So, but I made it for you, right? So use it for your own benefit, for your own enlightenment, if you want to call it, or whatever, for your own reference, okay? And please do not record the lectures in class or over Zoom, because I am recording that. So the last thing I want is my voice to be jumbled up from a recording on the phone and put online, and somehow saying, oh, we don't understand, Professor. Don't record anything. Look, I have a microphone here. I paid $10 for this thing. Okay, it gives high quality lectures. You've heard my YouTube videos. They're all high quality, so I will do that for you. I want you to just chill and enjoy what you're looking at and learn with me, okay? And with that, I hope we have a great semester.